In this video, we're going to talk about the giant planets. And if you're following along in the OpenStax Astronomy textbook, it's chapters 11 and 12. Now, which ones are we considering the giant planets? Jupiter, Saturn, Uranus, and Neptune. And we'll talk about Pluto and the other rocky bodies in the outer solar system and the asteroids in a separate video. So there's really two types. There's the gas giants, which are Jupiter and Saturn, and what we sometimes call the ice giants, Uranus and Neptune. Now, actually, all four of them are very, very similar. They don't have solid surfaces that we can stand on. It would be kind of like trying to stand on a cloud and you sink in. Now, they do get more solid, first to liquid and then to solid, as you sink in. You could think about the way the pressure in the ocean increases as you go down and down and down inside the planets. So there's no surfaces. So many old science fiction stories used to have, men from Saturn or creatures from Jupiter or whatever, and that wouldn't be able to happen because they don't have rocky surfaces. They all have very large magnetic fields, what we call magnetospheres. And we always think about Saturn and how beautiful Saturn's rings are, but they actually all have rings, although Saturn's are the biggest and the most prominent. Now, Jupiter. The atmosphere in the upper clouds, and what we can see in this cone here is it kind of shows you as you're going down and down into the planet. So the very upper clouds have a lot of ammonia and methane. And some of the ammonia actually freezes, so that it's actually like solid the way our clouds are. And then, as the pressure increases and increases, it gets so dense that hydrogen becomes a metal. Now, we only think of hydrogen as a gas here on Earth, but under really, really intense pressures, it can get squeezed so close together that it actually is a metal. And then we think that they do have ice and rock cores. One thing to notice about all the gas planets is because they don't have a surface, they don't have surface features. So we're not going to be able to talk about craters and valleys and things like that. Jupiter, though, does have different bands of clouds, and it has weather. And, of course, the most prominent feature is the Great Red Spot. All of the gas giants spin very, very fast, maybe even surprisingly fast. So their day is 9.9 hours. So when we have one day on Earth, they've had roughly, not they, but Jupiter itself has had roughly 2 days. It takes longer to go around the sun because of Kepler's law. It takes 12 years, and it's about 300 times as massive as the Earth, 318 Earths. So let's talk about that Great Red Spot because it's so prominent. All the giant planets have weather and they have winds. They get heating from the sun, but they also have internal heat from their rocky cores. And it turns out they're so far away from the sun that it's actually kind of a balance. About half of their energy comes from the sun, and the other half comes from this internal heat. So just like on the Earth, you have different areas where it gets heated more and less, and it can cause air currents. The same thing happens on the other planets. They have weather and winds. And then we have the Great Red Spot, which is this swirling storm or hurricane that's larger than the Earth. And it's been raging for about 300 years, this Great Red Spot, as far as we know. Now, it is shrinking. So eventually the Great Red Spot, I don't have a time frame for you, but it will eventually go away. Storms on Earth don't live 300 years, maybe a few days or a week at the most. The reason why the storms live so long on the gas planets is there's no continent. So on the Earth, these storms, their energy eventually is going to get, even the wind energy is going to get broken up and taken away by mountains and the land and the continents. But there are none. There's basically nowhere for it to go. It's kind of like swirling a milkshake. So it will just swirl and swirl and swirl, and there's nothing to dissipate the energy. So it's been about, we think, greater than 300 years. What's actually more interesting, maybe than the gas planets themselves, are their moons, because their moons have surfaces. Now, the four largest were discovered by Galileo. And I bring that up again because that was a big piece of support for the heliocentric or the sun-centered solar system. Because moons went around Jupiter, it seemed to suggest that everything doesn't really have to go around the Earth. To us, that doesn't sound surprising here, in the 21st century, but it was a big piece of knowledge or a big jump in science way back when. And as of this recording, there are at least 79 moons. We don't memorize them. Now, I'm a little bit older probably than most of you. I actually remember I memorized the moons of Jupiter just because I wanted to learn them when I was a kid, but I think there were only 12 or 13 that we knew of at that point. So the moons of Jupiter, Earth only has one, and they show our moon here just to give you an idea of the size, that they're all roughly the same size as our moon. Ganymede and Callisto are actually a little bit bigger. There's Io, Europa, Ganymede, and Callisto. And we'll talk a little bit about these major moons. So Callisto is the outermost Galilean moon, the one that's furthest away from Jupiter. It's about the size of Mercury. So Callisto really is almost a planet, but we don't call it a planet because it orbits Jupiter rather than orbiting the sun. But really, in terms of as a body in space, it's very similar to a very small planet. It's a little less dense, so we don't think there are a lot of metals there. We think it's mostly ice and some rock. But it's so cold that the ice is hard as rock. And if you've ever fallen and hit your head on ice or, on an icy pond or something, you know that it can be as hard as rock. And that ice is cratered like our moon. So that suggests there's no atmosphere and it gets bombarded a lot. Ganymede is actually the biggest moon in the solar system. And as far as we know, it's differentiated, that it has a rocky core and the outer is an ice mantle. So the core would be rock and then ice on the outside, maybe kind of like the pit and then the fruit of the avocado, just to use an analogy. And we can see, even in this big picture, you can see cracks. Or on this close-up, you definitely can see cracks, which suggests that there are some tidal forces here. Now, they're probably not plate tectonics, or at least not the way we would think of it on Earth, where the big masses of the plates on the Earth are moving. What it is it's closer to Jupiter. So as it moves around in an elliptical orbit, so here's Jupiter, and I'll try and draw roughly an ellipse. It's not great, but it'll do for Ganymede. Sometimes it's closer to Jupiter, sometimes it's further away. So sometimes it feels the pull of Jupiter very strongly, sometimes a little bit less when it's farther away. And it's kind of like kneading it like dough. So that's what we think is happening, that there's this tidal force, that as it's close to Jupiter, it's squeezed in, and then it stretches out a little bit, and that's what's causing the cracks on the surface here. And we're going to come back to that tidal heating in a minute. So Europa is also of Jupiter, and this one is really interesting. Jupiter's heat vaporized a lot of the water. So we see this thick crust of ice on the surface. And there are a few craters. It's not very cratered, which tells us that it's still very active. In other words, this ice formed recently. Much like there's very few craters in the Maria, the lunar seas, because we think there was lava activity recently. But because of all this cracking, can you see all these cracking on these ridges here? That's suggesting that there's a lot of pushing and pulling and stretching going on. And we think that there may be an ocean underneath Europa. There may be liquid water somewhere else in the solar system. And that's the first time we've seen that. Yeah, there's been a little bit of water in the Mars polar ice caps, a little bit on the moon, but this is the first time we're seeing the suggestion of liquid water. Io. This is the last major moon of Jupiter that we're going to talk about. It's the most active moon in the solar system. It's even more volcanically active than the Earth. In 1997, when they had an observer spacecraft up there, there were greater than 50 eruptions. And you can see in these little inset drawings here, the way they're blowing them up, those are volcanic eruptions on the surface. Now, what's causing those volcanic eruptions? Again, it's that tidal heating. As it gets closer to Jupiter, it gets squeezed, stretches a bit, and that gives it some internal heating. To use an analogy, if you've ever taken a rubber band and stretched it back and forth a whole bunch of times, it actually gets warm from that stretching process. Or the same thing, dough or clay. It warms up as you need it. And it's not only from the heat of our hands, it's that stretching and compacting that gives it what we would call tidal heating. Now, Saturn is, of course, probably the prettiest planet in the solar system, I'd say next to Earth. And its atmosphere is very, very similar to Jupiter's. It has ammonia and methane in its upper atmosphere. And then the hydrogen gets squeezed down and becomes metallic, and we think there's ice and rock at its core. Very similar to Jupiter. In fact, its day is only slightly longer than Jupiter, about 10.7 hours. It takes about 30 years to go around the sun. Remember, Jupiter was 12, Saturn's 30. It's the pattern. As you get further out, it takes longer. Now, it's not as big as Jupiter. It has a mass of 95 Earths. An interesting thing about Saturn is its density is only 0.7. Water's density is 1 gram per cubic centimeter. So if we had Saturn, and if we had a pool big enough, so water is 1 gram per cubic centimeter, Saturn would float. It would float like a beach ball, like a blow-up beach ball, right on the surface of this giant pool. But of course, we don't have one. So I think that's really neat that it actually would float in water. And we have to talk about the rings, because they're the most significant thing to know about Saturn, or the thing that makes it unusual. And you can see them even in inexpensive telescopes. Now, in an inexpensive telescope, you know, the kind you might buy as a starter telescope, like I'm saying, the kind a low-end one you might buy at Walmart or Kmart, around the holidays they have them. And I've seen this. I have a fairly inexpensive telescope, and you can see the rings. Now, not distinctly, not quite distinctly, but it kind of looks like a little stretched out saucer. And the rings organize themselves almost like the planets into different bands. And what are they made of? They're mostly ice. Some even call them moonlets. And it turns out they follow Kepler's law, but not with the sun at the center, but with the moon. So the further out the ice is, the longer it takes to go around. The inner ones spin much faster. Now, why does Saturn have rings and we don't see it on the other planets? Now, we do. They are there on Jupiter, Uranus, and Neptune, but they're really prominent on Saturn. So there's a couple ideas. One is the breakup hypothesis, that maybe there was this icy moon that Saturn had. Maybe it had a collision and it broke it up, and those little ice moonlets are orbiting Saturn. A similar thought is, where did the asteroid field come from, that we're going to talk about in another video. And others say, well, it's just a moon that never formed, that all this ice and dust may have been out there and it just never was able to come together and to form a little moon. And this is an artist's conception. So this is, somebody did a little, I guess it's a digital painting of it, where you can see that they have just these chunks of ice orbiting the rings of Saturn there. Now, we're not going to talk about all of the moons of Saturn, but one that's really interesting to talk about is Titan. It's about the size of Callisto. So it was discovered in 1655 by Christian Huygens, who was a very prominent in astronomy. And what's interesting about Titan is that it has rain and lakes on the surface. Now, the problem is, or the thing is, it's not water. It's made of ethane and methane, which are hydrocarbons. So ethane is C2H6 and methane is CH4. They're hydrocarbons. Hydrocarbons are just made of hydrogen and carbon. But it's unique in that there's surface weather on this planet. but it's probably too cold for life. And because Huygens was such a popular or important astronomer, they even named the lander in 2005. And it's significant because it's the only moon landing we've done in the outer solar system. So in terms of moons or planets that we've been able to land on, Titan is the farthest. We've sent satellites, other spacecraft to see further out, but in terms of landing, Titan's as far as we've put boots to soil, although they're robot boots. And these pictures are just, I think, stunning. That's why it's worth talking about Titan. If you look at the picture as they get farther and farther down, they look like mountain ranges. And if you didn't know and you showed this to somebody, maybe adjusted the color, there's no reason they couldn't say, oh, those look like mountain ranges here on Earth, maybe in a desert area, or maybe if we adjusted the color or something, in the Himalayas. The mountain ranges look an awful lot like Earth. And here's the picture from the lander. And again, that could be a desert or an empty field here on Earth, or it looks a lot like the surface of Mars. Here, what we can actually see are some of these lakes. So the blue spots are these lakes, but they're lakes of methane and ethane, of hydrocarbons. The most common hydrocarbons that we use here on Earth are gas for heating and cooking, or gasoline that we put in cars. You can almost think of these are almost like big lakes of gasoline, very similar to that. And then here you can see rivers and cracks running on the surface here. So it really is an amazing little moon because of its similarity to Earth, but it's not liquid water. A couple more planets in the outer solar system to talk to. The first is Uranus. Now, in this picture, you can see the rings that it has. Uranus is unique because of all the planets on the solar system, it's the only one that spins the wrong way on its side. It's almost 90 degrees on its side, spinning different than the rest of the solar system. And we think it probably didn't form that way. We've seen this before. Venus has a very slow day. And the explanation is there was probably a collision that slowed Venus down and changed its speed of rotation. Uranus spins with its axis the wrong way, or 90 degrees to the other planets. And again, we see the explanation is there was probably a collision with some other large object early in the solar system. And it has 27 moons. Seeing it again, upper clouds, mostly methane for Uranus. Spins very fast. In fact, its day is 17.2 hours. So it's just kind of amazing that all these gas giants are so big and they spin so fast. Its year is 84 years, and it's about 14 times the size of Earth. And now you're probably noticing we're starting to see more ice here. These are sometimes called the ice giants because if they're colder, they're further out, a little bit smaller, so we think that more and more of their core is made of ice. Still covered with clouds on the top. You couldn't stand on the surface of Uranus, you'd just sink through the clouds. Neptune and Uranus are extremely similar. They're almost like sister planets. Again, the upper cloud is mostly methane, which we use as natural gas for cooking and heating, if you have a gas clothing dryer, and then it goes to ice and rock. The day is almost identical. It's just about an hour shorter than what Neptune's or Uranus's is. 165 years and about 17 Earths. So it's extremely similar to Uranus. And a moon that we might talk about for Neptune that we know a little bit about and have some nice pictures of is Triton. It's, again, mostly rock and ice. Some people have even said, these moons of the outer solar system, they're kind of like a snowball with a rock in the middle of them. And Triton, we know, has water, nitrogen, methane, and carbon monoxide. So the nitrogen, the methane, and the CO, those are all things that we could possibly use to make an amino acid. Now, that doesn't mean there's life on Triton, but those are the compounds that are available. The water is mostly in ice here. However, there are very few craters, kind of like the moon. If you look here, we're seeing at least some craters in this mountainous region and fewer craters here. This almost looks like a frozen pond. So there's some suggestion that maybe the water does occasionally melt and refreeze here, kind of like the way the lava plains of the moon would prevent any, not prevent, but wouldn't show any cratering or not as much cratering. An interesting thing that we've seen on Triton is geysers, which we think are caused by the heat of the sun. Again, suggesting there may be liquid water underneath the surface here. And here's another view, and I think right here is where they're trying to show the geysers there. And we can definitely see here where there's fewer craters in certain areas. Probably these dark areas are kind of like the seas where there was melting and then refreezing.